Rest of chapter 10. Okay, so we're going to backtrack now that we've covered some of the other content and talk about sulfonate esters, because sulfonate esters, as a reaction unto themselves, not super useful, because no one wants to really make that as an end goal. But the reason sulfonate esters are really useful in synthetic schemes is because they solve the problem of alcohols being poor leaving groups. So if you want to do a substitution reaction on a carbon which contains a hydroxyl functionality, you have to do something to that hydroxyl to help it move along. And let's see here. So generally, what we're going to do is treat an alcohol with sulfonyl chloride. And what this is going to do is it's going to convert the alcohol to a compound which has a good leaving group, so you can do a subsequent nucleophilic attack on it. And what the reaction overall is going to look like and this is always done in pyridine, kind of like the other reactions that we were doing last class. And we're just going to kick off. And this is an interesting one because the hydroxyl is going to act as the nucleophile, attacking the sulfur, kicking off the chloride. So instead of this getting attacked or targeted for nucleophilic attack, this is going to be the target of nucleophilic attack, and the hydroxyl is going to initiate it. So that's going to be our product generally. There's a couple of different sulfonyl chlorides. The most common is tosyl or OTOS. So let's see, CL. So para, toluene, sulfonyl chloride, or tosylate chloride. So TS is almost always substituted. If you use, instead of drawing this whole thing, you can just say tosyl chloride, and that's fine because you don't need to memorize the individual R groups which differentiate all of these different sulfonyl chlorides. This one's super common, super commonly used, very effective. There's also methane sulfonyl chloride. And then there's a trifluoromethane sulfonyl chloride, where all three of the hydrogens on the methyl group are substituted with fluorines. And you guys can imagine that this, because of the electron drawing capacity of these fluorines, will enhance the reduce the electron density on the sulfur, which make it a better target for nucleophilic attack. So this can be a little more effective than this, probably. However, more expensive. So I've never used these two. I've used this one a couple times, and I've seen tosylates used more in the literature than these other two variations. Let's.
Can you remind me again what the circle inside of the hexagon?
Oh, that's right. We haven't done benzene rings. So because you have resonance, where the double bonds move, you can describe a benzene ring or any conjugated ring with a circle.
Is it incorrect?
No, it's not incorrect. Yes.
On the test, if this were to be a free response, would the one on your far left TSCL, would that be acceptable to use, or would you want us to?
If you're doing synthesis, yes. If you're actually pushing the arrows for a mechanism, you'd want to be doing this. But I'm not going to ask you guys for a mechanism on this, even though it's super easy as a mechanism. But I'm not going to have you guys memorize the structure of tosylate.
Can you tell us what that name of that third one is again?
That is the trifluoro methyl sulfonyl chloride. Trifluoromethane sulfonyl chloride. Mechanistically, let's go ahead and push the electrons real fast so that we can see, because there's going to be an important point to this mechanism that differentiates it from some of the other techniques that we've already covered. Here. So, like I said, we initiate with the alcohol being the nucleophile, attacks the sulfur, kicks off the chlorine. Now we've got this positively charged oxygen, which we deal with exactly the same way as we have before with pyridine. And now we've got a new leaving group. So we've gone to a good leaving group versus what was initially a very poor leaving group. And the reason this is a good leaving group, anyone want to take a stab at it? Under what conditions would we consider that super stable or pretty darn stable? Right, so if something comes in here and pushes the electrons to that oxygen, what we're going to have as a leaving group that looks like a 2, it should be an oxygen, is this. Why would this be a good place to put a pair of electrons?
Has lots of resonance.
Lots of resonance. We've got 3 good resonance structures where these electrons, because we have a formal charge here of negative. Oh. Okay, not doing that anymore. Can go down here, pushing these electrons up. Putting the negative charge on this oxygen, but these electrons can come down, push those electrons just as easily. So we have 3 equivalent structures, so we're basically able to distribute this negative charge over 3 positions. So each of the oxygens are only accountable for holding 1/3 of a negative charge. And because of this, as a leaving group, these sulfonyl tosylate are about 100 times better leaving group than chloride would be. So they're excellent leaving groups because of that resonance stabilization of the charge. So, how do we use these things? Well, any questions so far before we go into usage? Cool. Okay, so if we want to do any kind of nucleophilic attack on an alcohol, what we would want to do first, if we're going to use sulfonyl chloride, is take our alcohol and then react it with potassium chloride, pyridine, so now what we've done is converted the alcohol to something with a good leaving group, and then we can come in with our nucleophile of choice, and that nucleophile can do an attack and push off the leaving group and give us our substituted product plus this charged tosylate leaving group. So it's just an extra step in any synthesis where you are working with alcohols. Now let's see, what would some of the things we could use as good nucleophiles? Well, we could use cyanide, we could use anything with that lone parent charge is going to be a nice nucleophile we can throw at it. That one looks familiar. We've got lots of good nucleophiles at our disposal now, which would be perfectly acceptable ways to kick off a tosylate. So I'm going to put up an alternative approach to this, and then we're going to look at stereochemically why we would want to use one versus another. So we've got this really slick technique, but we've already done something like this where we talked about rationalizing why we would want to put a chloride, substitute a chloride. For hydroxyl, and that's because we can use the chlorine as a leaving group so easily, and because alcohols are cheap and plentiful frequently. So let's say we want to do a high yield, low heat reaction, and the first step we use PBr3. The bromine comes in, is substituted for this hydroxyl, and then we treat that, follow that with methoxy group. And what we should get following this, doing nucleophilic attack, kicking off the bromine, that's right, good, is this product. We do the exact same reaction or very similar reaction, and we use tosyl chloride with pyridine, and then follow that with methoxide. We have this one. So, big picture, we've done the same substitution, we've now changed the stereo centers. Here, we didn't invert the stereo center. Well, we did, but we didn't. Here, we did. So now, what we have is two techniques that give us control over the outcome of our stereochemistry, which is incredibly useful. I know, this is so great now.
Does the first one reverse it twice?
Yeah, it does. Yeah, because it's a pair of Sn2 reactions. So for the first one, this is an Sn2 style reaction. So what's going to happen is, well, this step isn't, but the subsequent attack is. because we get this kind of putting the mechanism in condensed form here. We get the initial attack forming where this attacks the phosphorus, kicks off a bromine. Pyridine comes in, scoops up the extra proton, taking care of the charge. Now we have this compound, that bromine that got kicked off, can then act as a nucleophile, do an Sn2 style attack, which is going to cause an inversion of the stereocenter. Because we're doing that backside attack because of the Sn2, so it's going to flip the stereocenter. And then when we come in with our methoxide, kicking off the bromine as a leaving group, this gives us a second Sn2 style reaction, reinverts it the other direction, pushes the R group back. And so we've got a pair of Sn2s, so we've inverted the stereocenter one way, then reinverted it back to its original. Because the tosylate reaction, or the approach we're using the tosylate, I'm going to break this down. So we'll do the tosyl chloride with pyridine. The initial attack on the tosylate kicking off the chlorine is with the hydroxyl. So this is initiating here, but we don't get a second attack with the chlorine coming back. So oh, good. So because this does the initial attack, this stereocenter doesn't invert. Because these electrons are coming over here, nothing's happening over here yet. So there's been no change to the stereochemistry on the tosylation reaction. However, when we come in with our, put it up here, methoxide, and do our second, or our first substitution, that is Sn2, we are going to get that inversion. That's going to be our product. So we now have control. If we want to keep a particular orientation of a stereocenter, we can. By taking an alcohol, converting it to an alkyl halide, and then doing a targeted substitution on that alkyl halide. Or, if we want to invert stereocenter, we can use the tosylation. And if it's not attached to a stereocenter, then you can use either. I'd probably use this one because it's a better leaving group and it's really easy to do. So they're both great. Actually, I'd probably use whatever I had handy on the shelf, because they're both good approaches if you don't have to control your stereocenter. It's funny that you got so excited about that, because I actually wrote on my notes. So I'm glad I'm not the only one who thought that was great. This is a great point to come back to something that happened in the last class. Erase this. Any questions? Actually, before we change gears, questions. Yeah.
Okay, so in the first one here, in the one up here, you didn't put pyridine
No, I didn't.
with the first condition. Is that something you would want to write in?
Yeah.
Okay. Oh, thank you. This is like suddenly just showed up.
Yeah, because this doesn't work without pyridine, because
Okay.
pyridine swoops in.
Because you need pyridine with both strategies here.
Does anyone have a question about down here before I erase it to answer that first question? No? Okay. we go.
Like that error message is not gonna
So, yeah, so to get rid of that positive charge, you have to have the pyridine acting as base, pull off that hydrogen, put that back on,
So you
and
kind of just skip that step in the mechanism that you do?
yes.
Okay. You just assumed it happened.
Yes.
You made it happen.
We make it, we made it happen.
Okay.
Force of will. And then, once that's gone, then the bromine that got kicked off can come in and do the Sn2. Yes.
So if you're doing this in real life, do you have to add the methoxide after you've added the
Yeah.
pyridine? Okay.
So when you see this, we're condensing it. Say, step 1, do this. Step 2, do
If
this.
you put it in at the same time with the methoxide, act as a base also and pull the hydrogen instead of pyridine.
It's pretty darn good base, and you probably have, yeah, that would be. Let's see, what would happen if you put hydroxide? It would be bad. Don't do it.
Don't do it.
2 steps. Step 1, create alkyl halide. Step 2, substitution reaction of alkyl halide. I mean, what happens when you put a strong base on an alcohol, based on the last lecture? What can happen?
That was your lesson.
Oh. Ah. And you didn't watch the video? I'm just giving you a hard time. I know, because the view count's really low, so you would have been an anomaly.
It's actually pretty entertaining to watch one of them. I actually see faces of people with commentary in the background.
Oh, okay, because I see, not from, because like, I've been posting the video of the class. How's this happened? No, but no, you understand that you have faces to go with the voices.
Especially over here is pretty
Thank you.
Okay. Any other questions? I think we
questions.
no other questions? Okay. Yeah, last class was pretty sparse with the ice thing, but we're all acclimating.
You didn't finish your question.
Yeah, you didn't
about
answer your own
what
question.
happens if you have a strong base to an alcohol?
Yeah, what happens?
None of us know.
Deprotonate the alcohol.
You can. Yeah, if you have a really strong base, you can because what this is.
Was it the dehydrated?
So what is this?
Wait, was it the hydrolysis? Was it?
It's methanol, where a really strong base created methoxide. So if we had this happening to a primary, if we had some secondary alcohol and this came in acting as a strong base, you would have an equilibrium system where now you would be having a base strong enough to. Pyridine is a good base, but it's not a strong base. So it's good enough to clean up that proton because you want to take the proton, move electrons onto the oxygen, but you don't want to base it so strong that you can start abstracting protons from other hydroxyl groups as part of an equilibrium. That's super worse leaving group. Yeah. Yeah. And then it would act as, anyway, yeah, lack of clarity would ensue. So you definitely want to keep that as 2 steps. Would run around deprotonating things willy-nilly. Anything that's remotely decent acid would be like, eh. Okay. Oh yeah, getting on to that mistake I made in the last lecture, kind of. I didn't include it in my notes, but there was something with the constraints of SN2s versus SN1s on alcohols. What was it? So we have tertiary, secondary, primary, and I believe primary, did I say primary is SN1 only, and these two are SN2 only, or did I have this?
1 and 2 were SN2, 3 was SN1.
I'm sorry?
1 and 2 for Sn2, and then 3 is Sn1.
Yeah, you're backwards.
Yeah.
Oh, thank goodness. Okay. There we go. Okay. So I had 1 and 2 as Sn2, and these two as Sn1. Okay, that's what I said. Is that what the book says or what I said?
The book says.
The book said this, so I got it right this time? Okay.
What I have is you said that primary can do Sn2 without heat, secondary has to have heat to do Sn2, and then tertiary is.
This still needs a little bit of heat to kick off the Sn1 to get the carbocation to form.
The book also said that secondary can undergo Sn2
And I looked into that a little bit. So this is a little bit different. This is specific to alcohols. Generally, if we're talking about the alkyl halides, what we covered before is correct. The difference here is that once you've converted the alcohol to water, this is a phenomenal leaving group versus better than a bromine or chlorine. Those are good leaving groups. This is a phenomenal leaving group. So what we've done is we've changed what's happening a little bit in the secondary zone because our quality of our leaving group's gone up so much. So it's easier to form the secondary carbocation because, let's say we've got the secondary alcohol, and if we convert that with sulfuric acid, now this is really good at spontaneously taking those electrons because the product is not H26, water.
That works.
So because this is such a great leaving group, the combination of stability of these as the products versus the stability of this as the reactant is what's important. So even though this is less stable, this as a pair, as a system, is more stable than this as a system because this is so much more stable than this. So that's why we're seeing a little difference between what's happening here with alcohols and what's happening with alkyl chlorides or alkyl halides in general. Sorry.
The difference there is just that.
The real world's complicated.
So the difference there is just that because H2O ends up being the leaving group, it's easier for secondary carbocations. Okay.
Whereas, because you do have a little bit of a steric issue here that's not resolved. And so if you access it, it's still a great leaving group, but accessibility doesn't change when you're doing the Sn2. So you still have that little bit of steric hindrance that is slowing it down. So then, because this doesn't have a steric issue, and now we have a better leaving group, it ends out, and this is the preferred mechanism for alcohols.
So what you said is the alcohol, the one with H2O is both of them together are more stable, therefore it's better.
Right, because it's always about the system stability versus one particular thing. What's happening net as the reaction. So this is preferred over this because this is a better leaving group because these are the same. So. Okay. Oh, yeah, we have plenty of time to finish this up. This is great. So, now, despite me making fun of the criticism that I do seem to be randomly hopping about the chapter, it does feel a little bit random. because now I'm going to pick up where we left off.
Which place?
Last lecture.
Okay.
So, because I thought Toslitz would make more sense if we did a few other reactions that involve pyridine first. Because I felt like it. That's why.
People who wrote the textbooks are wrong.
It's all just a matter of opinion. This is the 4th textbook I've taught OChem out of, and they all have pros and cons. Like, there's an oxidation I'm not including because I've never seen it before, and I know for a fact it's not going to be something that's on a standardized exam. Each book has to throw its little curveballs of content in that differentiates it from the other books, and they have to do structural changes that differentiate it from other books. Like this book decided that it was smart to put aromatics in chapter 8, even though nobody does that. But then because of that, they include a bunch of examples that involve aromatics in subsequent chapters. So we have to ignore those examples. So it's just... But we taught it in the first semester or first year we had this book. We just taught it straight through and then realized we're dedicating all this energy to conjugated systems and benzene chemistries that aren't something that anyone's going to see on the ACS exam, and we wanted to align our curriculum more with ACS. So even though we liked the book, we decided to move the chapter, even though it creates some small problems with the material in these last 2 chapters. Yeah.
Sorry, can you just repeat that again, what we don't have to study from
Chapter 8.
Okay, but then you said there are subsequent examples, so you said there was an ozone.
The stuff we are not finishing on this chapter,
Okay.
I'm specifically excluding because of the leaning on aromatic rings. And then there's like osmium tetroxide is a reaction where you produce a pair of hydroxyl groups across what was a double bond. And it's weird as a reaction because, I mean, it's a good reaction and people include them, but in content. But the issue with like doing osmium tetroxide is, for some reason, even though having 1,2-diols is occasionally useful, it's not as central as the other things we're covering. And the second you say osmium tetroxide, when somebody takes a guess for some reason, students just love it. And they will guess osmium tetroxide on like half of their unknowns. And I don't understand like what the attraction to it is. But we're not going to include some of the ends of this chapter. We're focused on alcohols.
So for C, it's not what it is.
There are so many reactions not included in, like I said, some of the, like this book includes thionyl-chloride as a mechanism dealing with alcohols under general conditions, whereas McMurray doesn't, even though it's commonly used. There's so many reactions and reagents in OChem that you're always going to have like a subset of it anyway. So you don't want to, can't have a comprehensive OChem 1 experience that covers everything, because that would be terrible. So we just have to make a call at some point as to what we're going to include and what we're not going to include. Even though something could appear on a standardized exam that wasn't included. Although, if you wanted insight into what that exam might include, the ACS study guide would be a really good way to go. American Chemical Society. Yeah. They're the ones that write all of the standardized exams for all the chemistry classes. So, let's see. So let's see here. So let's say we have a situation where we would think we would be doing an E1 style reaction, but E1 requires harsh conditions, so heat, high acidity, and is subject to rearrangement, and so might not be able to do the reaction we want because this would have unintended consequences on some part of the compound over here, or because of having a tertiary or a quaternary carbon adjacent to the alcohol we're working with, we could end up with rearrangement issues. So because of this, we need an alternative if we can't do a classic E1. And what we do is just play the game, and we're going to actually convert the E1 to an E2 mechanism by changing the quality of the leaving group. And what that looks like is if we have a secondary alcohol, so just cyclohexanol, what we can do is replace with POCl3 and pyridine at 0 degrees Celsius, so on ice. Keep it cool. We want to keep it mild here so it doesn't go wild. And what this does is, oh, this is reversible, sorry guys, is very similar, where we come in here, attack the phosphate, kick off chlorine. Now we have, ooh, there's an oxygen in there. Sorry, skipping steps. Let's just do the mechanism. Might as well just do the mechanism. Mechanism or no? Do it. Okay, let's just, okay, well, instead of breaking it down, we'll do it. Just the reaction. Dehydration reaction / elimination. But instead of being E1, it's going to be E2. And the mechanism okay, so we're going to get TAC, leaving group, pyridine, grabs that proton, breaks the bond, pushes the electrons up to satisfy that positive charge on the oxygen. If you look at this, if this bond were to break, pushing the electrons over here, onto that oxygen, skipping steps, we have a negative charge here. That negative charge can be distributed by resonance up to here as well. So we have 2 points of resonance. And because we have a pair of halogens, their electron withdrawing as well at all times, and would help carry the burden of some of that as well. So this is an excellent leaving group. And then if I draw in our 2 hydrogens we've got here, ammonia comes in as a base a second time, grabs that proton, pushes those electrons down here, breaking that bond, treating that as our leaving group, and that gets us our product there. So that is our way to do an E2 by making an excellent leaving group, which facilitates it. And this is all mild conditions. It's done at 0 degrees Celsius for the whole reaction, so you don't have to worry if you have a compound that's thermally a little unstable. Fantastic way to do a targeted elimination reaction. You can also just do a tosylation if you want to. That's the other way you can do this. I could do this exact same reaction, do tosyl chloride, use some strong base afterwards, because it's not going to be a one-step, and we get our OTOS in the first step. So this would be 1, and then bring in the strong base. The base is going to come in here, grab a proton, kick that off as a leaving group, and give us the exact same product. So either of these approaches is perfectly acceptable. It's nice to have lots of ways to do things because in the real world, it's not uncommon for one of them to work better than the other, depending on your compound. Yeah.
So in the first example, pyridine is acting as a base
2 times.
2 times.
Yeah, because it's the solvent also. So there's lots of it available.
Okay. Why couldn't you do the same thing for the second one? Where pyridine acts as a base the second time.
Well, this is going to be a stronger base, so I'm guessing this needs a little bit more initiative to kick this off. This is a pretty darn, this is a stable product unto itself. Even though it's a great leaving group, it's a pretty stable product. So you're going to need to use a stronger base to grab that proton to initiate kicking that off as a leaving group versus this one where it can leave with a weaker base. So if you want to do some one-pot chemistry and you had some pyridine handy and you had a distillation apparatus to keep your pyridine super dry, which I assume you'd have, then yeah, this would be a great way to go. If you happen to do a lot of tosylation reactions or super comfortable with tosylation reactions mechanically, this might be preferred.
So is that oscillation reaction inserted or does...
2 steps.
Okay. So
2 steps. So 2 steps. Yeah, 1 step, 2 steps.
So the first step is the reaction with the TSCL, right?
Yes.
Okay.
So
The last part, I mean, is that...
And what's preventing the methoxide from just doing a substitution with the...
because it's a really strong base.
Okay, so it is...
So it's going to prefer the elimination because you're going to have that competition like you always would in this example. So there could be a little bit of substitution product, but it's going to prefer the elimination product. Another reason that this might be better because you have this mild base doing it, that's also not a fantastic nucleophile.
How are we considering this a one-step E2 when there's 2 arrows here? I'm confused. You call that a concerted reaction, but there's 3 different.
1 pot. What, wait, 1 step E2? What? Who said that? No, I didn't.
You just said it was a concerted reaction.
This one?
Yes.
It's all in 1 pot, so it's 1 step in terms of what you did in the laboratory, not mechanistically 1 step. Yeah. So you put your reagents in and you get your product versus having to do a multi-step.
So concerted reactions E2 is only relevant in alcoholides.
So if you can't do the E1, but you want to do an E1 style reaction, you have to change the leaving group. Once you've changed the leaving group, you can do an E2 style. So yeah, it's all about having a quality leaving group. Without having to use a whole bunch of sulfuric acid and reflux, high heat, stuff like that. No carbocation, so there's no carbocation rearrangement. The last part of this chapter that we do need to cover is oxidation of alcohols. So the book, which I totally agree with, excludes mechanisms for these oxidations because other books do include them. I don't think, like some of our previous mechanisms that we've excluded, I don't think they provide a lot of predictive power for other mechanisms later that you need to know. So things like pyridinium chlorochromate, very unique mechanism, not going to have a lot of carryover. I want you guys to be able to use it in a synthetic scheme and predict it, but I'm not going to ask you mechanisms for these oxidations. So, if we've got an alcohol, this oxygen can be targeted for oxidation a couple of different ways. And there's 3 general categories of products we can get from those oxidations. If you have a primary alcohol, like this, series a bit more. If you do the oxidation on this, the first oxidation is going to be an aldehyde. The second oxidation possible is a carboxylic acid. Because it's on the end of the carbon chain, there's room to add another equivalent of water over here. If we have a secondary or higher order, the first oxidation gives us a ketone. So those are our 3 possible outcomes. And because we already have 4 bonds here and no hydrogens that can get kicked off with another unit of water, this cannot go to a carboxylic acid. So if you have primary aldehyde carboxylic acid as a 2-step, some oxidations will take you all the way to here, some reagents will take you here and then stop here. You can use a great strong oxidizing agent here, and it will stop here. So those are our 2 different general, or 3 general scenarios for oxidation of alcohols. And this is going to be super important because a ton of our content next semester is going to be carbonyl chemistry, which is chemistry of nucleophiles attacking these carbons. There's a whole chapter just on carboxylic acid chemistry. So we want to have tools to go from alcohols to here synthetically so that we can utilize all the tools we're going to cover next semester. So how do we do it? Let's talk about those tools. Okay, so the first reagent is chromic acid. TrO4, not dichromate. Chromic acid is the reagent, but what you actually put into solution is sodium dichromate in the presence of acetic or sulfuric acid. And under high acidity, sodium dichromate becomes chromic acid, and this is what reacts. So, in a synthetic scheme, even though this is what you would do in the laboratory, you can just write chromic acid. If you want to substitute chromic acid with sodium dichromate and sulfuric acid, that is correct, and you can do that, but I'll take either. Because you can't buy this. You have to do this to make it in solution. So I'm just going to work on the assumption if you put this, that this is how you'll get there. This is fantastic for converting secondary alcohols or non-terminal alcohols to ketones. Really good oxidizing agent of alcohols. If you use this on primary. This will go all the way to the carboxylic acid. You can't stop the reaction. So you will transiently produce, even if you have one, you wouldn't want to go with one equivalent here. You'd want to run a logarithmic test, because if you had one equivalent, you'd have a mixture of products inherently, where some of this would then get consuming this, and you'd have some of this, and some of this. So you don't want to go with one equivalent. You want to use a substantial excess, so that you convert as much of this as possible to this, and as much of it as possible to this. So you'd only use chromic acid or sodium dichromate in acid if you want to make an aldehyde with a primary alcohol. If you want to stop the reaction here, you use a different reagent called pyridinium chlorochromate, or PCC. So PCC has some voodoo to it, and you always use PCC in dichloromethane, so it would look like PCC in CH2Cl2 dichloromethane. And if we were, say, doing the exact same reaction of a primary alcohol, this one will stop at the aldehyde. Unless your dichloromethane isn't super dry. So in lab, what you're going to find out is even these solvents like chloroform and dichloromethane. I know this because I actually did this reaction as part of my master's degree, and I made the carboxylic acid, and I did that I think 3 times. So my PI did his monthly, attended his monthly lab visit, and came in and it's like, well, how's it going? I'm like, it's terrible. PCC is stupid. It says that it's going to stop at an aldehyde, but it goes all the way to the carboxylic acid every single time in high yield. And he's like, well, you dried your dichloromethane, right? Like, I opened a new bottle. He's like, you dried the dichloromethane, right? What? So, the reason this stops here is because the solvent doesn't have extra water in it. It's a very strong oxidizer, and if there's any water in your solvent, that water will provide the extra oxygen for the subsequent oxidation to the carboxylic acid. So, not only do you have to open a nice new one, you use molecular sieves, which pull all the trace water out of solution, and then the reaction stops at the aldehyde. So, it's not the PCC being a weak oxidizing agent that stops it here, it's the solvent. So, let's see here. What about if we want to oxidize T-Butyl alcohol? Yeah. So this carbon has no hydrogen. Notice that to do this carbon has to lose one of its hydrogens, and for the subsequent reaction to carboxylic acid, you lose the second hydrogen. If you can't lose this hydrogen, you can't do the oxidation. Because this has no hydrogen to lose, this cannot be oxidized to a ketone or anything else. Also, this is kind of the common sense. What's wrong with that? 5 bonds to carbon, No bueno. Minus 50. Right. Okay. Tentative laugh. Yeah, don't do that. So, if you see this, oxidize this tertiary alcohol. Right. It's a trick. We would never do that. It's like dividing by 0. Okay? So. Let's see. Oh, geez. 2 minutes left. Hypochlorous acid. So these chromium compounds are expensive to dispose of because they're a little toxic. So hypochlorous acid, HOCl, which you produce with sodium hypochlorite in the presence of acetic acid at 0 degrees Celsius. What sodium hypochlorite? Bleach. Funny story, I spent the better part of a day trying to find this in the chemical stop room at UAF. Couldn't find it. I was and then I went to the person who runs the chemical stock room. She's like, I know we've got it. She spent an hour on it. Decided it was time to Google it. We both slapped ourselves. Sodium hypochlorite bleach. So you'll see all kinds of papers. Use a 5.25% solution of aqueous sodium hypochlorite. Wow, that's incredibly specific. That's the standard concentration of normal bleach. Ultra bleach is 6.0%. So that's what makes it ultra, is it's got extra that in it. But you put this with acetic acid, you get this. This is what's doing the oxidization, and let's say we've got some secondary alcohol. We put sodium hypochlorite and acetic acid in there. It will oxidize this to a ketone, and if you do it with a primary alcohol, just bring this back down here, it will actually stop at the aldehyde. And we don't have time to do the mechanism. The mechanism is super easy. I'm sure you can rationalize it.
Are you missing a carbon?
Yeah.
Probably. There's a high likelihood of it. Up here? Yes.
And the second time as well.
Yeah.
That's what happens when we're trying to make up time.
Oh.
Yeah. Yeah, that's acetic acid is
It's like, oh, I really see.
that. We gotta have that carbon. So that is, I have a funny story about trying to use this for synthesis and it didn't work. But that doesn't mean that it can't work. It was an anomaly. So I'm gonna call it good so people can get to their next class. If you have a question, go ahead and come on up.
Do we always have to write in the